Math 230, Cuesta College, I'm Joe Vasta, and we are covering section 6.6, Permutations and Combinations. And in the last section, we learned the formula for permutations and combinations. We did those without repetitions. So let's go ahead and do some problems. Before we do some problems, here are the puzzles for this lecture. What goes in the boxes? So you know, look, you have this like 1, 8, 3, 4, 8, 6. Okay, so some number goes in there. So there's the first puzzle. And the second puzzle. And of course you can pause the video and think about it, and we'll give you guys the answers at the end. What goes in the boxes? And the hint is it's probably going to be A's, B's, and C's. So let's get rid of this, and we'll do that at the very end. An ice cream shop has 5 different flavors. How many different ways can you order 3 scoops on a cone without repeating flavors if order matters? So order matters happens to be a permutation. No reps, no repeating flavors. We're starting off with 5 different flavors. And you want to order 3 scoops on a cone. So we have 5, pick 3. This is what we covered in the last section, how to crank these things out, and so that's what I'm going to do. 5, pick 3 is 5 times 4 times 3. The countdown starts at 5 and it has 3 numbers in the countdown. 1, 2, 3 numbers. So let's see what this gives us. 20 times 3, 60. So there's the answer. Problem number 2, very similar situation. We have 5 different flavors. You cannot repeat flavors. How many ways can you order 3 scoops on a cone? Order does not matter. So when order does not matter, this is a combination. We are doing combinations without repetitions. 5, choose 3, which we can find on Pascal's triangle. Go to row 5 and we move over 3. 1, 2, 3. The answer is 10. So there it was. We use countdown formula here, and we use Pascal's triangle here. Now if you wanted to see me crank this out with the formula, I'll do that really quickly. We don't really need to do that for a problem with small numbers. 5 choose 3 is 5 factorial on the top, 3 factorial on the bottom, and then you need another number here that will make it so both of those numbers add up to 5, so that's a 2. 5 times 4 times 3 factorial. We go to the biggest one. Here's a 3 factorial. And a 2 factorial is 2 times 1. The 3 factorials cancel. They become 1s, and the 4 and the 2 become 2 over 1. All 1s on the bottom. On the top we have 5 times 2 times 1, which is 10. So I won't be doing a lot of that in 6.6. If the numbers are smaller, we could just take care of this using Pascal's triangle. Let's move on to the next page. I think the hard part about this section is determining whether this is going to be a permutation or a combination. And you'll see. Now things are going to get a little bit different than ice cream examples. Problem number 3. A certain committee is to have a president, vice president, and secretary. If 9 people are available to serve on it, how many different committees can be selected? So what I'm going to do, starting on these examples, is I'm going to represent the things that we are selecting using X's. So, for instance, there's 9 people. I'm going to make those 9 people be X's. 3, 4, 5, 6, 7, 8, 9. Okay, and in all these problems, you're going to have some X's, and you're going to be selecting some of those X's. So in this problem, those X's represent people, and you are creating a committee to have a president, vice president, and secretary. So let's go select those. President. So I just randomly picked one. Vice president, okay, how about this person? And secretary. Now, as I was selecting those, was I putting different labels on them? And the answer is yes. I was putting different labels on these. I said president, then vice president, then secretary. And so that would mean the order in which I picked those people to be on this committee, that order does matter, which makes order matters a permutation. Okay, so how do I know it's a permutation? Because we had different labels on the selected items. Also know that most of these problems we do in 6.6, there are no repetitions. So let's say this is like Bob, and we picked Bob as the president. Well, we couldn't pick Bob as the vice president. So repetitions, we can't repeat flavors, or we can't repeat, in this example, people. So no repetitions on these ones. It's a permutation because if Bob's the president and Mary's the vice president and Charlie is the secretary, well, if we said Mary was president and Bob was vice president and then Charlie was still the secretary, that is a different order, and that does matter. That gives us a different thing. So that's why order matters. Which makes this example a permutation. And since we had 9 items, we're going to say 9, pick 3. So let's go ahead and compute that. This is going to be 9 times, there's a countdown that starts at 9, and it has 3 numbers in it. 9, 8, 7. I believe we did that calculation in an earlier section of chapter 6. I think we got 504 for that. So there's 504 ways that can happen. I don't know what happened there. Okay, and so this is how you can do these problems. I found that when I started teaching this class using X's and circling them, it clicked a lot better. You know, because I think the way I was taught is you just think about, does order matter? And that's not always the simplest thing to do without some visual. Problem 4. A certain committee is to have 3 members. If 9 people are available to serve on it, how many different committees can be selected? Well, now we still have 9 people, just like the last problem. So I'm going to go ahead and put 9 X's. And we are going to select 3 people. So listen to what I say as I'm circling to these X's. Committee, committee, committee. Was I putting different labels as I was circling those guys? No, I was saying the same exact thing. So we could say we have the same labels on the selected items. So if we have the same label on the selected items, What would that say about order? It would say that order doesn't matter, or does not matter. Now why is that? Because if this is Bob and this is Mary and this is Charlie, and I say, you're on the committee, you're on the committee, you're on the committee, and point it that way, it's the same as saying, hey Charlie, you're on the committee, Mary, you're on the committee, Bob, you're on the committee. I'm saying the same thing. So the way I'm labeling these guys who get put on the committee, they all have the same status, so order really doesn't matter in terms of how I select them. When order doesn't matter, we found that that was a combination. So 9, choose 3. Now with combinations, we're going to use Pascal's triangle. We're going to go to row 9 and count over 3. Row 9, so I put my pen on entry 0 and I'm going to count over 3. 1, 2, 3. The answer is 84. And that's basically how you start your homework in section 6.6. Let's go ahead and do another problem. There it is. From 10 raffle tickets in a hat, 4 tickets are to be selected. The holders of the winning tickets are to be awarded free trips to Hawaii. How many ways can the 4 winners be selected? So, the first thing is, we start off with 10 people, or 10 raffle tickets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So look at this. I'm going to select 4 of those tickets, and what I'm going to be saying is this: Hawaii, 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 Hawaii. Was I putting different labels on those as I was circling them? No, it was the same label. It was Hawaii for all of them. So what does that mean? That means same labels on the selected items. This means order doesn't matter. If order doesn't matter, then this happens to be combination. And what are we going to do with that combination? Well, we're going to say 10, choose 4. 10, choose 4. We'll find that on Pascal's triangle. Go into row 10 and counting over 4. 1, 2, 3, 4. The answer is 210. Okay, let's do the next one. From 10 raffle tickets in a hat, 4 tickets are to be selected, just like the last time. The holder of the first ticket wins a car. So notice what I'm going to do. Notice what I'm saying as I circle these. Car. The second, a motorcycle. Motorcycle. The third, a bicycle. Bicycle. And the 4th lucky person gets a skateboard. How many ways can these prizes be awarded? So was I putting different labels on the X's as I was circling them? Yes, I was. It would make a big difference to you if you won the car versus winning the skateboard. So since I was putting different labels on them, what does that say about order? That says that order matters. And if order matters, that makes this a permutation. Notice there's no repetitions here. You don't pull out a raffle ticket and then pull out the same raffle ticket. So we have permutations, 10, pick 4. So countdown starts at 10. There are 4 numbers in your countdown. 10, 9, 8, 7. We saw from earlier that 9 times 8 times 7 was 504. Of course, this is multiplied by 10, so this is 5040. And that's how you do problem number 6. So the hard part, especially if you've already done your homework in 6.5, the hard part of this homework is deciding whether it's going to be a combination and a permutation. And if you use this little X scheme and circling some of them, hopefully that will make it a lot simpler. Next 2 problems, 7 and 8. So problem 7. A math teacher with a class of 10 students wants to give 6 F's and 4 C's. How many ways can he do this? Well, that's not fair, but who cares about fairness? This is math. Math has no feelings. So I'm going to go ahead and put 10 X's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm going to go ahead and select some things. So what am I going to be selecting with this? Why don't we select the people who pass, the people who get C's? So as I do this, listen to what I'm saying. Am I putting different labels on the ones I'm circling? Okay, so what if your teacher just went like eeny, meeny, miny, mo, and he randomly selected the passes? That would be kind of sad. Okay, so but here it goes. That's what I'm going to do. So this person right here, you get a C. And then let's see, this person gets a C. This person gets a C. And this person gets a C. Was I putting different labels or the same labels? I was actually putting the same labels on there. So if I was putting the same labels on there, then that tells me that order doesn't matter. Now you might be thinking to yourself, what about the people who got F's? Well, they're not on the committee, are they? They were not chosen, so by default they get F's. Order doesn't matter. That makes this a combination. 10, choose 4. And on Pascal's triangle, well, we did that in problem number 5, but 10 choose 4. 1, 2, 3, 4 is 210. Okay, so I want to show you something that will completely blow your mind. Okay, so you're selecting here, you're selecting the C's. And then by default, the other people get F's. So watch this. I don't even know if I have space to do this, but I'll do it in blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What if we said, let's select the F's to be on the committee, and then the people who not selected get C's. So this guy gets an F. F, F, F. That guy gets an F. That guy gets an F. Did I get 6 of them? 1, 2, 3, 4, 5, 6. So I'm selecting the F's. It really doesn't matter which ones I circle, really. And so order doesn't matter because I said F, 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 which makes it a combination. 10, choose 6. Now on Pascal's triangle, we had 10 choose 4, but 10 choose 6 would be 1, 2, 3, 4, 5, 6. You get the same answer, 210, because we have the symmetry of Pascal's triangle. And in fact, the other problems that we did that involved combinations, like the raffle tickets and the people going to Hawaii, we could have selected 6 tickets out of the hat and say, you guys are not going to Hawaii, and the other 4 by default would go to Hawaii. So what it seems like what combinations do is they take a group of people, we'll just say people for now, and what the combinations do is they partition those people, they partition them into 2 groups. And that's what it does. We didn't want to say that like on problem number 2, but that is what it's doing. It's partitioning a group of people or a group of ice cream flavors into 2 groups. And in this one we saw F's and C's. Now here's one that's a little weird here. A math teacher with a class of 10 students wants to give 6 F's, 1 D, 1 C, 1 B, and 1 A. How many ways can you do this? Let's draw the 10 students. Get back to the black ink here. 7, 8, 9, 10. Okay, so how are we going to do this? Well, we don't want to pick the 6 F's, okay, because that's going to kind of ruin things. What we want to do is we want to pick these guys. We want to pick the first person. So who's it going to be? We don't know. How about this person right here? You get an A. Then the next person gets a B. So look, you get a B. And then the next person gets a C. And then this person gets a D. And by default, the rest get F's. So those are the 6 F's right there. Now, was I putting the same label on the ones I was circling or different labels? Well, if you go back and listen to it, it was different labels. I said, the first one I circled, I said A, and then the second one I circled, I said B. So those are different labels, which means order matters. Oh, it sure does if you're a student getting an A opposed to the student getting a D. So order matters, which makes this a permutation. We have 10 in our class. We're going to say 10 pick 4. And that's how we're going to play the game. 10 pick 4 is 10, 9, 8, 7. The countdown starts at 10. There's 4 in the countdown. In fact, this was identical in terms of the permutation to problem number 6. So we ended up getting 5,040 when we did that multiplication. And so this is how we do these problems. Now, coming up, if we have time in one of our lectures, I don't know if it would be this lecture or then another lecture, we could actually explore what would happen if it had said like 4 F's and 2 D's and 3 C's. You know, we could explore that, but right now we don't know how to do that. We only know how to do these kinds of problems. Okay? And some of you don't care for the more complicated problems, and I may or may not do that. Let's go ahead and do problem number 9. Problem number 9. How many ways are there for John to invite 2 of his 7 friends to dinner? Okay, so he's got 7 friends. And there they are. John wants to invite 2 of them to come to dinner. So this is what we're going to say. Okay, come to dinner. Come to dinner. Was I putting different labels on those as I was circling them? No. Both of them are dinner. So this would say that order doesn't matter, which makes this problem a combination. to go 7, choose 2. We'll use Pascal's triangle. Go to row 7, move over 2 times, 1, 2. So that is 21 for the answer. So hopefully you're getting this. You might have already started pausing the video to see if you can do each problem. We're going to go ahead and do number 10. A cook wishes to select 3 spices from the spice rack containing 8 spices to enhance the flavor of the soup. How many ways can this be done? So as you can see, our problems are not coming in pairs anymore. They were for the first 8 problems. So I mean, this could be a permutation, it could be a combination. We have to decide. How many X's am I going to put up? Well, 8. Here's the spice rack right here. 1, 2, 3, 4, 5, 6, 7, 8. And so, instead of being people, these 8 X's represent different spices. So I'm going to select 3 of them. And as I circle them, look, you're going in the soup, you're going in the soup, you're going in the soup. Good thing these X's represent spices instead of people, because that would be a little gross. So was I putting different labels on those? No, I was putting the same label on all 3 of those. So that tells me that order doesn't matter. When order doesn't matter, we see that we're working with a combination. And this is going to be 8, because there's 8 X's there. Choose 3. How are we going to compute 8, choose 3? We're going to go to Pascal's triangle, row 8, move over 3, 1, 2, 3. So this is 56. So please, when you're doing your homework, well, please do your homework, and when you're doing your homework or taking the test, don't be that person that goes like this, oh, 8, choose 3, and then just count this as the first one. So I've seen some people go like this, 1, 2, 3, and they get 28 for the answer. No, this is entry 0, so that's why we go 1, 2, 3, which is our 56. Well, we're going to continue with this. Six runners enter a race. How many ways can first, second, and third place be decided, assuming there is no tie? So here's the 6 runners. Okay, so they're wondering how many ways first, second, and third can be decided. Well, let's go ahead and circle some of them. Let's say this one came first. First. Second. Third. Was I putting different labels on those? The answer is yes, I was, which means order matters. Order matters tells me that this is a permutation. So let's go ahead and do the correct talk for this. This is 6, pick 3. So this vocabulary where we say 6, pick 3, we're only going to use that in this class. Now if we had 6, choose 3, that's universal for combinations, and we said that last lecture. 6, pick 3. Countdown starts at 6, and there's 3 numbers in the countdown. 6, 5, 4. 6 times 5 is 30. 30 times 4 is 120. There's the answer. Okay, the next one here. Dad has 8 different DVDs on his shelf. He will let each of his 4 kids select one DVD. how many ways can the DVDs be selected? Okay, so this is a bit different from the last problem. And some of you might go, oh, well, let's put 4 X's out because there's 4 kids. Well, then there's 8 of these things, and that would be kind of crazy to select 8 from 4. So what we really want to do is put the 8 DVDs, make them be represented by X's. So 1, 2, 3, 4, 5, 6, 7, 8. There they are, the 8 different DVDs. Now let's say, just for the sake of argument, that this family, they have the dad, and then let's say their kids are Steve, Tom, Steve's the oldest, Joe, Bill. And because Steve is the oldest, he gets a double portion. No, I'm just kidding. Because he's the oldest, the dad's going to let him select first. And you know, you've got movies like maybe The Terminator, and maybe this one over here is like The Sound of Music, etc. So Steve gets the select first, and when he selects them, it doesn't say it in this problem, but he gets to keep it forever. That's part of his inheritance. So wow, how great is this? So Steve's looking at the 8 DVDs, and we circle this. And guess what? That goes to Steve's room. And then who comes next? Tom. And then Joe. And then Bill. He looks like the good ones have already been taken, and so Bill's like, I gotta take this one right here. Now, as I was circling these, I was saying the names of the kids. Now, this didn't have these names. We could have just said first kid, second kid, third kid, fourth kid. Kind of like first, second, third. And so I am putting different labels on the X's that I'm circling because they're going to different kids' rooms, or they're going to belong to those different kids. So this would mean that order matters, which makes this a permutation. 8, pick 4. Usually, out of all these problems I do, this is the one people hate the most, because they're like, it's a combination, but really it's a permutation because I'm putting different labels on the circles. Even if I didn't use those names and I just said first child, second child, third child, fourth child, I'm putting different labels on there. So let's go ahead and do our countdown that starts at 8 and has 4 numbers in the countdown. 8, 7, 6, 5. So it looks like I have 8 times 7 is 56. 6 times 5 is 30. Carry the 1, so that's 18, 15, 16. So it looks like there are 1,680 ways that the DVDs can be selected. We're going to continue with some more problems here. Now that problem number 13, that little thing you see right there, that's a little calculator icon. I've been able to do, 1 through 12 without a calculator. This one I would not attempt to do without a calculator. Could I if I had a lot of time? Yeah, I just don't want to multiply a whole bunch of numbers together. Well, what are they asking here? It says, how many 5-card poker hands are there? Okay, well, we've got to figure that out. And to figure that out, we've got to first realize, well, how many cards are there in a standard deck of playing cards? Well, there are 52. Now, I could start drawing 52 X's. In fact, that's what I'm going to do. I drew out 52 X's here to represent the 52 cards in the deck of playing cards. Now the question is, when I'm dealt 5 cards, Does order matter? Well, if you don't play poker, suppose you were dealt this. Well, this is probably a good hand. It's called the full house. When people play poker, and they're not showing everybody, I'm just showing you guys this, you could rearrange your cards. And so there it is. So it doesn't matter which order I'm dealt the cards, because once I get them in my hand, I could rearrange them all I want. So 1, 2, 3, 4, 5, order does not matter, which makes this problem a combination. 52, choose 5. Now, if you were curious what to push on your calculator and you just had a basic 4-function calculator, I'm going to kind of go through this, but some of you might want to skip ahead. You would have the 52 factorial on the top, 5 factorial on the bottom. 52 minus 5 is 47 factorial. So this is 52, 51, 50, 49, 48, almost didn't fit at 47. Factorial. This is all over the 47 factorial. And then 5 factorial is 120. I could have gone 5, 4, 3, 2, 1, but I'm just trying to finish this up really quickly. And so on your calculator, you could go 52, 51, 50, 49, 48, multiply those all together, and then divide by 120. What are you going to get for this? Well, you're going to get this. So I'll put the answer right here. You're going to get 2,598,960 possible 5-card poker hands. So it's like over 2.5 million, and only 4 of those hands are royal flushes. So this is interesting if you play poker. Combinations might interest you. Our next problem. Flip a coin 7 times. How many different ways can the outcome have exactly 3 heads? Now you might have remembered these problems from chapter 1. We're going to go ahead and take a look at this. When you flip a coin 7 times, or you can flip 7 coins, let's just put the 7 coins right here, and we'll make the 7 coins be represented by these X's. So these are 7 different coins. Here's the first one, the second one, the third one, the fourth one, the fifth one, the sixth one, the 7th one. And look what's going to happen. They're asking how many different ways can the outcome have exactly 3 heads. So guess what? Let's say the 7th coin I flipped was a heads. And then look at this. Heads. Heads. Am I putting different labels on those? No, I'm not. So guess what? With flipping coins, order doesn't matter. And when we say order doesn't matter, that's in how I'm circling the ones that are on the heads committee, and by default the other 4 are on the tails committee. So this right here happens to be 7 choose 3. So when we did this in chapter 1 with Pascal's triangle, we were really doing combinations. You go to row 7 and count over 1, 2, 3. The answer is 35. And so that's why Pascal's triangle works for those problems in chapter 1. We didn't really want to get into it back then, but now's the time to do that. How many different bit strings of length 7, so that's 7 zeros and 1s, or 7 bits in a row. So how many different bit strings of length 7 have exactly 3 zeros? So here are 7 bits. There they are. Those are 7 bits. And you're trying to count the ones that have exactly 3 zeros. So guess what? I'm going to circle some of these and say, okay, you're on the 0 committee. You're on the zero committee. You're on the zero committee. Was I giving them different labels? No, I was giving them the same label. The other guys who did not get circled, by default, they are ones. So guess what? Order doesn't matter when they ask a question like this, because as I was circling them, I was saying the same thing. Now, we're not saying that when you have a bit string of length 7 and you go like 0, 0, 0, 1, 1, 1, 1, as opposed to 1, 1, 1, 1, 0, 0, 0, that those are the same thing. We're not saying that. When we say order doesn't matter, we're saying the order in which I'm circling these three, I'm not putting different labels on them. That is what I'm saying. So this is going to also be, like the last problem, 7 choose 3, and we see the answers right there, which is 35. So there it is. Problem number 15. Let's go ahead and do a few more problems. An ice cream shop has 5 different flavors. Okay. How many different ways can you order 3 scoops on a cone if order matters? I've highlighted order matters, which means this problem here is a permutation. But this happens to be the first time in this lecture where we say repetition of flavors is allowed. Hopefully that doesn't look like I'm crossing it out. I'm trying to highlight that. So repetition of flavors is allowed. This is a permutation, and with all the permutations, and I probably didn't say this, but with all permutations you have in this class, you could always use slots. So I'm going to turn this ice cream cone to the side. What did we say? We're going to do 3 scoops on the cone. I know that's going to ruin your ice cream. Here are some slots. 1, 2, 3. And so how many choices do I have for the bottom scoop? Well, it's 5 different flavors. I have 5 choices. How many choices do I have for the middle scoop? 5, because we can repeat. And for the top scoop, 5. So this happens to be, if you want it to be a math nerd, 5 cubed. But in any case, when you're computing the number, you're going 5 times 5 times 5. 5 times 5 is 25 times 5 is 125. So there that is. Now, number 17 has a calculator. It says an ice cream shop has 5 flavors, so it starts off the same. How many different ways can you order 8 scoops on a cone if order matters? So once again, this is a permutation. And it says repetitions are allowed. So look at this. 1, 2, 3, 4, 5, 6, 7, 8. I mean, that's quite a big ice cream snack there. And under each of these slots, you're going to put a 5. But what's happening? I mean, this is a lot of 5s to write. I think hopefully there's 8 of them there. It doesn't even line up with the ice cream. Oh well. So this really is 5 to the 8th. Of course, there's a calculator there, so we would do that on our calculator, and we'd end up getting 390,625. Well, here's the deal with these last 2 problems, and let's just take a look at this one. I'll do this in a different color. This happens to be a permutation. You start off with 5 flavors, and you're going to select 8. Now you might have heard me say earlier that this number should never be less than that number. That was when you did permutations where reps are not allowed. But when reps are allowed, sometimes there's notation where there's a capital R there. And so there it is. When reps are allowed, that's what this thing becomes. So in general, if you wanted a formula for reps being allowed, you don't have to write this down. You can go like this. You can say permutations where reps are allowed, n comma r. Well, what is this going to be? This is going to be n to the r power. Okay, and that is the formula for permutations where reps are allowed. Okay, but we don't need all this fancy stuff. We just, when we get permutations, we can just draw some slots and go from there. So let's go ahead and do some other problems. What I do for 18 and 19, this is completely an extra part of this class, and some of you might want to just stop the video or skip ahead to the answers to the puzzle. Some of you are not going to appreciate this, so this could be dangerous to your health here. But I'm going to do this anyway because there are some people in the class that want to know how to do a problem like this. An ice cream shop has 5 different flavors. How many different ways can you order 3 scoops on a cone if order does not matter? So this makes it a combination. And repetition of flavors is allowed. So reps allowed. What I'm going to show you is going to be really cool. We don't know the formula for this. I mean, so what we're really looking for is we have how many flavors? We have 5 flavors. And we are going to choose 3 of them. But reps are allowed. We do not know the formula for that. So that's capital R there. So, wow. So this is not going to be on the test, but this is just something that's pretty weird. So how am I going to do this problem? Well, 5 different flavors. Let's go ahead and put the flavors here. Let's say this is chocolate, vanilla, strawberry, this is mint chocolate chip, and let's do Rocky Road. Okay, so let's go like that. So watch this. So you might say, hey, I'm only allowed to order 3 scoops. I want 2 chocolates, because reps are allowed, and a mint chocolate chip. So that's one person's order. Now someone else might say, hey, I want a vanilla, mint and chip, Rocky Road. And then another person might come along and say, hey, I just want 3 strawberries. 3 strawberry scoops. Okay, so we have that right there. Okay, so this is what I'm going to ask you to do. We're going to go on the first person's order, and we're going to kind of come across here and tell me what you see first. You see a scoop, and then you see another scoop. So let's put the scoops like this. Then I see a partition here, so I'm going to just put that partition right there. There's nothing there, and then another partition, and then nothing there, and another partition. A scoop, a partition. Okay, so that's the first person's order. The second person, what do you see? Partition, scoop, partition. Partition is just the fancy word for the border. I'll just say border then, I guess. And then another border. Scoop, border, scoop. So look at this person's order here. Border, border, scoop, 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 border, border. It's almost as if this ice cream shop was set up like this, where you had to say your chocolate, vanilla, strawberry, mint, and rocky road, you know, you had to say them in that order. It's almost as if you can say, you know, scoop, scoop, border, 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 scoop, border, or you could say, you know, those look like zeros, 0, 0, 1, 1, 1, 0, 1. Or the second person can say 1, 0, 1, 1, 0, 1, 0. What do these look like? These are bit strings of length 1, 2, 3, 4, 5, 6, 7, of length 7. But each of these bit strings of length 7 have how many scoops, or how many zeros? 3 zeros. So we find this right here, that if you are doing combinations where reps are allowed, 5, 3, that actually equals combinations where no reps are allowed, so the ones we've been working on, 7, choose 3. And if you go 7, choose 3 on Pascal's triangle, 1, 2, 3, we end up getting 35. So the thing to take away from this is the formula for combinations with repetitions. N, R. Well, which one looks the same here? Well, it looks like the 3 is just right there. And then this right here, 5 plus 3 does not equal 7, so this is what it's going to be. It's this. N plus R minus 1, R. And so that's the formula. This is going above and beyond the level of this class, but I thought I'd show some people this because, you know, maybe you're interested in it and maybe you're not. So let's go ahead and do one more problem that has that. The ice cream shop has 5 different flavors. How many different ways can you order 8 scoops on a cone if order does not matter, which makes this a combination? And repetitions are allowed, so reps allowed. So look at this. This is combinations where reps are allowed. We have 5 flavors to select from, and we are going to select 8 of those. Now we couldn't have a bigger number here if reps were not allowed. So using this formula here, it's going to be what? It's going to be 5 plus 8, that's 13, minus 1, so that's 12. 12, choose 8. Now my Pascal's triangle only went up to row 10, so maybe you can confirm this answer on your own. 12, choose 8, whether you use Pascal's triangle or the formulas, is 495. So we've covered in the last 2 extra credit like problems combinations where reps are allowed, a little bit more complicated. There will actually be people who get a degree in math who will never see this. Okay? And if you understood this development where we went scoop, scoop, border, 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 scoop, border, and you saw the connection there, this is called an isomorphism. I was taking a class where they did this, and more than half of the people in the class did not understand what the teacher was doing. For one thing, the teacher was not using ice cream as an analogy, and that's probably where a lot of people got derailed. Let's go ahead and do our puzzles. So we are finished with 6.6, the puzzles. Which one did we do first? I don't know, we'll just do them in any order. So here it is. What goes in the boxes? Well, the mistake is, and I was misleading you when I went like this, because a lot of you were probably like, oh, we have to figure out a pattern here. The pattern is reading it across. So look at this. 1, 2, hey, that's like doubling. And then 4, 8, it is doubling. 16, 32, 64, 128, 256, 256 times 2, 10, 11, what is that for? 5, 12, look at that, 5, 1, 2, so that's 5, 12, and then we're going to double this one, so 4, 2, 10, 10, 24, so there it is, 210, 210 goes in those boxes. Let's go ahead and do the last puzzle. Some of you are probably not going to like this. What goes in there? Look what this puzzle has. Start off right in the middle, sort of in the middle, A, B, C. A, B, C, 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 A, B, C. Uh-oh. We've got to think outside the box. A, B, C, 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 A, B, C. And then, so what goes in the box then would be, well, got to learn how to use a pen. A, B, C, A, B, C, and I was writing from right to left, so it almost looks like it's just the row, the same row that's right above, and that's a coincidence, and so you spiral and get the answer. Well, that concludes 6.6. I'll see you in the next video.